Now that we're done with our review of pre-calculus, we're ready to slow down and actually get into some business calculus that we've been waiting for so long. And to start setting this up, we're going to start talking about an example. We're going to start talking about the function f of x equals x squared minus x minus 2 over x minus 2. And one thing you might notice about this function looking at the denominator is you can tell that it is undefined at 2. In other words, f of 2 is undefined. Because if we were to plug 2 into this fraction, we would end up with a 0 in the denominator, and that's not acceptable. But here's kind of the question that we're going to look at today with this thing called a limit, is instead of worrying about being undefined at 2, we really don't care what happens at 2. Well, we're going to look at what happens close to 2. In other words, we're going to find f of 1.9, or f of, let's get even closer, 1.99. Now, f of 2, we've already said, is undefined, so there's not going to be any value there. But maybe on the other side, f of 2.01, or f of 2.1. If we plug these values in for x, what numbers do we end up with? What happens when we are close to the number 2? Well, we're going to use our calculator to help us out with that. And the way we're going to do that is we're going to hit the y equals button. Put the numerator in parentheses. That's x squared minus x minus 2. And then I'm going to close the parentheses. Divided by, parentheses for the denominator, x minus 2. And I'm going to close the parentheses. Next, we're going to change some settings. To do that, we're going to hit second. And then the window button, above the window button, you'll see it says table set. And we're going to scroll down to the independent variable and tell it to ask, enter on ask for the independent variable. In other words, it's going to ask us what we want to plug in for x, and it's going to tell us the answer for the entire fraction. So now to look at the table itself, we'll hit second, and right above the graph button in the top right, you'll see the table option. It's asking us what we want to enter in for x. So let's start with the first option I had on there was f of 1.9. So if we put 1.9 in for x, y1 is 2.9. Then we'll type in the next one. We wanted to find out what f of 1.99 was. And when we do that, it says y is 2.99. 2.99. Now f of 2 is undefined. That gives us an error like we expected to see, because we already know that makes a 0 in the denominator. But if we put in 2.01, we end up with 3.01. And if we put in 2.1, we end up with 3.1. Now, what's interesting is this value in the middle that is undefined. It seems like when we come in from the left side, we're getting closer and closer to the number 3. When we come in from the right side, 3.1, 3.01, we are also getting closer and closer to the number 3. The way we express this mathematically is we are going to say, we'll make this number 1, we're going to say what's called the limit as x approaches 2 from the left side, this little minus sign, that means we're coming from the left side, from the negative infinity side. If we come from negative infinity and get closer and closer to the number 2, f of x gets closer and closer to the number 3. We call this the left limit. Coming in from the left side, x gets closer and closer to 3. Similarly, if x comes into 2 from the right side, notice we do a plus to represent from positive infinity to the right side, as opposed to negative infinity on the left side, of f of x coming in from the right side, 3.1, 3.01, 3.001, it's getting closer and closer to 3. We call that the right limit. What's important is that both of these are the same. Coming in from the left side, coming in from the right side, both sides seem to be approaching the same value. And so what we will do is we will say the limit as x approaches 2, as x gets closer and closer to 2 of f of x, the entire function from both sides is getting closer and closer to the number 3. And that's because both sides are the same. So we're going to talk about this thing called a limit. In fact, let's make an informal definition. Of a limit. Why do we do an informal definition? Well, here's a pop-up that shows you the formal definition. Ew. We're going to save that for the engineers to play with in a year-long calculus course that involves proofs. We're not going to go there. In this business calc class, all you need to know is as the x gets closer but not equal to some number a, then f of x gets closer to the limit L. How we'll write it out is we will say the limit as x approaches a of f of x. If the x value gets really close to a, not equal to, but close to it on both sides, the answer is going to be L, the limit. And there's lots of ways to calculate and work with limits. We're going to go over a couple of those strategies here so we can kind of see how that works. The first, most basic strategy is if we can plug it in. If we can plug the value in, we can find the limit. In other words, if we were asked to find the limit as x approaches 7 of the square root of x minus 3, well, we can actually plug 7 in for the x. That's going to be the square root of 7 minus 3, which is the square root of 4, which equals 2. And so the limit here is going to be equal to 2, because nothing fancy happens there. Here's another example. Let's say the limit as x approaches negative 2 of the absolute value of x plus 1. Well, again, we can just plug that negative 2 in for the x. We have the absolute value of negative 2 plus 1, which is the absolute value of negative 1. Absolute value is the distance from 0. We know that's a positive 1. So if it's possible for us to just plug in the number, that's great. We will just plug in the number. However, if you remember the problem we started with at the very beginning, we could not plug in the number because we would have ended up with 2 minus 2 is 0 in the denominator. It would have been undefined, so we couldn't just plug in a number. So we need another plan to help us when we can't just plug in a number. In fact, most of the time with what we'll do in our calculus class, you cannot just plug in a number. So we may have to simplify first. Let's go back to our original problem, where we're looking at the limit as x got close to 2 of x squared minus x minus 2 over x minus 2. Simplifying first, not doing the limit first. So the limit as x goes to 2, the numerator can factor. That's x minus 2 times x plus 1. The denominator is still x minus 2. And so you can see those x minus 2's divide out, and we're just left with the limit as x goes to 2 of x plus 1. Now, when we plug the 2 in, now it is no longer undefined. Because it's no longer undefined, we plug the 2 in and get 2 plus 1, which equals 3. And that agrees with the answer that we came up with earlier when we were just plugging values that were close to 2 into the function. However, this doesn't always work. Sometimes the limits don't exist. Some limits do not exist. And one way that happens is if we have a different value on each side. Remember, with the example at the beginning, we looked at the left side and got 3. We looked at the right side and got close to 3. Same value on both sides, so we said the value must be 3. But that doesn't always happen. Let's take, for instance, the example taking the limit as x goes to 3 of x plus 2 over x minus 3. Now, we can't plug 3 in because that would make the denominator 0. That's undefined. That's bad. We can't factor, so we might try the strategy we did before where we'll look at 2.9, 3, and 3.1. Well, we know 3 is undefined. We just want to see what's happening on both sides. So we'll go to y equals. Clear that out. And in parentheses in the numerator, we have x plus 2 divided by, in parentheses in the denominator, x minus 3. And when we hit second table, we don't want these numbers clear. Can I clear out answers? Nope, they don't want to clear out. Delete. Delete gets rid of them. Okay, so the first value we wanted was 2.9. That gives us negative 49. The second one we want is 3.1. That gives us positive 51. Notice those are nowhere near each other. If you think about the graph for this, we know from our previous lessons that there's a vertical asymptote at 3. And the graph is going to go a horizontal asymptote at 1. The graph is going to go down to negative infinity on the left and up to positive infinity on the right. They're going different directions. And because they're going different directions, we will say that the limit does not exist, because they are not going to the same final solution. So that's our informal definition of the limit, going to the same value on both sides as we get close but not equal to the number. It's nice when we can plug the number in, though, but if we can't plug the number in, we'll need to do some simplifying. But here's a few more rules for limits that can help us with some simplifying. And some of these are obvious when you think about them. It says, yeah, that would make sense that it would work. So we're going to do a proof by, yeah, I guess that makes sense. Let's say if we want the limit as x goes to some number of two things that are added together, f of x plus or minus some g of x. Well, what's nice about limits is if we want the limit of two things that are added together, we can take the limit as x goes to a of the first piece, f of x, and either add or subtract the limit as x goes to a of the second piece, g of x. So take the limits of the parts and then either add or subtract them together. Similarly, if we had the limit as x goes to a of two things that are multiplied together, f of x times g of x. We can do the limit before or after they are multiplied. So if it's easier, we'll first take the limit as x goes to a of the f of x and multiply that by the limit as x goes to a of g of x. Take the limit of the parts and then multiply the answer together. It also works with division. So add, subtract, multiply, divide. It doesn't matter. The limit as x goes to a of f of x divided by g of x. Take the limits of the parts. The limit as x goes to a of f of x. And divide it by the limit as x goes to a of g of x. Take the limit of the parts and then divide the answers. Here's another nice trick. If we want the limit as x goes to a of some constant, some number, so there's no variables in there, of f of x, that constant is not going to change the limit at all, so we can pull that constant out and just take the limit as x goes to a of the function, and then multiply by the constant afterwards. One last rule, we'll take the limit as x goes to a of f of x, and then we're going to raise the whole thing to some constant power. Again, there's not much order to a limit. Sometimes it's convenient to first take the limit as x goes to a of the function, and then take the answer to some exponential power. So a lot of the times we can use these rules of a limit to take the limits of the pieces because it's easier to work with the pieces and then do the arithmetic with our results from the pieces. So let's take a look at some real simple examples where we see these pieces used to help us calculate some limits. Let's try. Well, first let's give us some definitions. Let's say the limit as x goes to 2 of f of x is equal to 5. And we'll also say the limit as x goes to 2 of g of x, another function, is equal to negative 3. Okay? We're going to attempt to find out what the limit as x goes to 2 of f of x minus g of x is going to be. Well, we don't know what f minus g is going to turn into. But what we do know about limits is sometimes it's easier to take the limit as x goes to 2 of the pieces of the f of x and the limit as x goes to 2 of the g of x. And then we'll subtract what's left. The limit as x goes to 2 of f of x is 5. That's what was given to us. Minus the limit as x goes to 2 of g of x is negative 3. Well, gee, that gives us 5 plus 3. The answer, clearly, is 8. How about this one? We can even figure out the limit as x goes to 2 of 7 f of x g of x is going to be. Well, 7 is just a constant. We're going to bring him out front. He's not going to have any effect on the limits. F of x times g of x will take the limits of the parts. The limit as x goes to 2 of f of x times the limit as x goes to 2 of g of x. And so we've got a 7 times x going to 2, that's 5 on f of x, times the limit as x goes to 2 of g of x is negative 3. That's going to be 110, 105. Yep. 7 times 5 times negative 3 is 105. So the limit as x goes to 2 of 7 times f of x times g of x is 105. Let's look at another trick. What you're going to find with limits, and where we're going here soon with these things called derivatives, don't worry about that word yet, is there's a bunch of little simple tricks. So think about it like we've got a tool belt, and we're adding tools to your tool belt. We want you to learn which tool to grab at what time and how to use that tool to get your solution. So here's another trick for your tool belt. Rationalize with a conjugate. You might remember this trick from algebra when we had a plus b times a minus b. The plus and minus in the center would subtract out, and that would just leave you with the square of the first term minus the square of the second term. And that was really nice when we had square roots. We got square roots out of denominators by multiplying by conjugates. Well, now what we'll do is we'll use this trick to multiply by a conjugate to get rid of an inconvenient situation. If we have the limit as x goes to 4 of the square root of the square root of x minus 2 over x minus 4. Now what you might notice here, we can't just plug 4 in for x, because if we do, we end up with 0 in the denominator. That's bad. That's undefined. There's no factoring that we really can do to reduce, but maybe we could get rid of that square root in the numerator. Now, I know in algebra we always rationalized in the denominator, but there's no reason we have to camp out and give all of our love and attention to a denominator. We can also play with the numerator. The conjugate of the square root of x minus 2 is the square root of x plus 2, changing the sign in the middle. Remember, to maintain balance, we do the same thing in the numerator and in the denominator. Now the numerator, don't lose the limit. The limit as x goes to 4. Now in the numerator, that's going to result in this middle stuff subtracting out to 0 because of the plus and the minus. So we've got the first term squared. The square root squared is just the x, the inside stuff, minus the second term squared. 2 squared is 4. Keep the denominator factored, though. X minus 4 times the square root of x plus 2. This is real nice because now we have a factor in the numerator and in the denominator that's going to reduce out. Because we were able to rationalize with the conjugate, we now have the limit as x goes to 4 of, don't forget the 1 in the numerator. Common error is people will put the square root of x plus 2 and nothing else. The x minus 4 does not disappear. We're dividing by x minus 4. Anything divided by itself is 1. We still have a 1 in the numerator times the square root of x plus 2. Now this is nice because we can actually plug the 4 in. It was undefined at the beginning. 4 minus 4 is 0, but now when we plug 4 in, it won't be undefined. Now we have 1 over the square root of 4 plus 2, and now we're in business because the square root of 4 is 2. We have 1 over 2 plus 2, which is 1/4. We've got the limit. So we know that as x gets closer and closer to 4, this function's going to get closer and closer to 1/4 on both sides. So that's another trick for your tool belt. So far in your tool belt, I want to review what we've got so far. First trick we have is we can just plug the value in. That's our first trick. Second trick we have was number 2, simplify first. Maybe we can reduce the part that's undefined. Third trick, maybe we can use some of our limit rules to make it an easier problem. Fourth trick was to rationalize with the conjugate. So there's 4 tricks we've seen so far. One last thing I want to look at with limits, and that is that idea of limits at infinity. So now we're going to say, what is the limit as x goes to infinity? Or what is the limit as x goes to negative infinity? Essentially what we're asking is what happens in the long term to the function. Does it go up forever? Does it go down forever? Or does it get to a point where it gets closer and closer to a number? In other words, we are looking for the horizontal asymptotes. And the way we find that horizontal asymptote is we are going to divide by the highest power on x. Oh, and use one more little detail. This is important. We're going to let you know that the limit as x goes to infinity of 1 over x to the n. If you think about this, what we're saying is 1 is a very small number and x is a very large number. X is going to infinity. We have 1 divided by a lot. If you have 1 loaf of bread to feed an infinite number of people, you have to divide it up evenly. What's everybody going to get? Pretty much everybody's going to get nothing. Because it gets divided up so small. That 1 loaf of bread divided up so small, nobody gets anything. You really have not solved world hunger by splitting up your loaf of bread. Okay, so we're going to combine these two concepts together. We're going to divide by the highest power on x, and 1 over x, that limit is 0. So let's find the limit as t goes to infinity of 5t squared minus 3t plus 7 over 2t squared plus 8. Notice we cannot find this limit by just the plug it in method, because we can't plug infinity in for the t. Infinity does not work as a number to evaluate in a function. So we need to use this strategy where we're going to divide by the highest power on, in this case, t. Notice it goes up to t squared, so we're going to divide every part by t squared. So divide by t squared, divide by t squared, divide by t squared, divide by t squared, divide by t squared. We're going to divide everything by t squared. So now we have the limit as t goes to infinity. Notice in the first term, 5t squared over t squared. The t squareds are gone. We're just left with 5 minus t over t squared. That's going to leave a single t in the denominator, 3 over t, plus 7 over t squared. There's no reducing there. All over, the t squareds divide out again, so we're just left with 2, plus 8 over t squared. Now we still can't plug infinity in for our t's. But we're going to go back to using our limit properties that we talked about earlier, where instead of trying to take the limit of the entire thing, we'll take the limit of the pieces and then add and subtract what's left. So we're going to take the limit as t goes to infinity of 5 minus the limit as t goes to infinity of 3 over t plus the limit as t goes to infinity of 7 over t squared, all over the limit as t goes to infinity of 2 plus the limit as t goes to infinity of 8 over t squared. Don't forget, number 1 up here on the screen, the limit of 1 over x is always equal to 0. So the 3 over t, that's 0. The 7 over t squared, that's 0. The 8 over t squared, that's 0. All that's left is the limit as t goes to infinity of 5 in the numerator. Well, gee, if t is going to infinity of 5, there's no t's in there. It's just 5. There's no variable to plug anything in. We don't care. It's just a 5 regardless of what t does. Minus 0 plus 0, that's 5. In the denominator, t goes to infinity of 2. Well, that's just 2 plus 0. So the limit as t goes to infinity of this entire fraction is 5 halves. The long-term behavior of this fraction is 5 halves. As the variable gets closer and closer to infinity, the function's going to get closer and closer to 5 halves. Now, I won't make you show all this work. What a lot of people do is they stop at this blue line up here and they say, well, gee, the 3 over 2, the 7 over t squared, the 8 over t, those are all going to go to 0, and so we're just left with 5 halves. If you want to do it that way, I'm okay with it. I'll let you get away with that. Let's do another example, though. Let's do the limit as x goes to infinity of 7x plus 2 over 3x squared minus x plus 1. In this guy, the highest exponent is squared. So we'll divide by x squared, 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 divide everything by x squared to find what our new limit as x goes to infinity is. 7x over x squared, that's going to leave us with 7 over x, plus 2 over x squared. All over, the x squareds divide out, we're just left with 3, minus, reduce an x, we have 1 over x, plus 1 over x squared. And you'll see the 7 over x is going to go to 0. The 2 over x squared is going to go to 0. The 1 over x goes to 0. The 1 over x squared goes to 0. What's left in the numerator is 0 over what's left in the denominator is 3. Everything else is 0 when x goes to infinity. 0 divided by 3, 0 is on top, that's okay. That is 0. And the limit of this function as it goes to infinity is 0. Let's try one more. Let's do the limit as x goes to infinity of x cubed plus 2x squared minus 3 over x plus 4. Same strategy we're going to employ on this one. We're going to divide each term by the highest exponent, and that would be x cubed. So we'll divide by x cubed, divide by x cubed, divide by x cubed, divide by x cubed, divide by x cubed. When we do that and reduce, we have the limit as x goes to infinity. X cubed over x cubed, that's 1. Plus 2x squared over x cubed. The x squareds divide out. We have 2 over x. Minus 3 over x cubed. All over. Dividing out an x, we've got 1 over x squared. Don't forget the 1 on top. Plus 4 over x cubed. Again, we'll notice that any x's in the denominator are going to go to 0. 2 over x goes to 0. 3 over x cubed goes to 0. 1 over x squared goes to 0. 4 over x cubed goes to 0. Which means what we're left with is a 1 in the numerator and 0 plus 0, or 0 in the denominator. But what do we know about 1 divided by 0? Can't have 0 in the denominator. 1 divided by 0 is undefined. Which means this limit is undefined. This function has no long-term behavior. It's not going to a specific number like 0 or a specific number like 5/2. This one is completely undefined. It's going somewhere completely different. So that kind of wraps up our discussion on limits. I'm going to talk about something that's related to limits and pretty simple to wrap it up, called continuity. But before we do, I just want to review one last time our strategies for limits. The first strategy, plug in the value. The second strategy, see if you can simplify first and then plug in the value. We do that if something's undefined. Third strategy, use the rules for limits to make it simple. Take the limits of the pieces and then do the operation second. Our next strategy was maybe we can rationalize with a conjugate. If there's a square root, think about rationalizing. Maybe that'll make things easier. And then our last thing we did was we looked at limits at infinity divided by the highest power of x, and then we looked at what that did to our expression. One last concept to wrap up today's lesson. It's a little bit simpler, called continuity. It's more of a vocab word at this point. I want you to be aware of what this vocab word means. We're going to look at some applications of what it means also. But basically, a function is continuous at C, at some number C, if two things are true. Number one, f of C is defined. It's nice if it's defined, because then we can take the limit as x approaches C of f of x, and that should be the same thing as just plugging the value of C into the function. So what does this look like? This is the case where plugging the value in solves the problem, basically. It's defined, f of C, and the limit at that point is that value. Well, let's look at a graph here. We'll go 3 left and right. And we're going to put a vertical asymptote at -2, a horizontal asymptote at 1. We're going to have a really funky function. So on the left side, we'll do the predictable loop. On the right side, it'll come up from -infinity. But at -1, we're going to have a hole in the graph and a solid dot up here at 2. But it's going to continue to come over here and up to 1. Then it's going to jump up to 2 and come down and level out at that asymptote. So what we're going to ask is this continuous at these values? X equals 2. At 2, right here, is it continuous? Notice it is defined at that point, and the limit, what it's approaching on both sides, is the same at where that point is. So the idea is, as it gets close from the left, gets close from the right, and it's actually on that point, it is exactly equal to the same value. Very predictable, nothing fancy happening. We say, yes, that guy is indeed continuous at 2. Let's back up. What about 1? What is f of 1? Well, f of 1 is down here at 0. So, yeah, f of C is defined. F of 1 is defined. It has a value. However, what is the limit? Coming from the left side, we're coming in close to this value at 0, but coming in from the right side, you notice the graph is up high. It's not coming to the same point. It's coming into two different points. What we've done is we've violated the second rule that the limit is equal to the value, because this one doesn't actually have a limit at all. So at 1, no, it is not continuous. We call that a jump discontinuity. It does not work there. Let's back up to x equals -1. Notice at -1, the point, the value, is up high at 2. However, the limit, where the graph is getting close, is down here. Notice the limit is at a different point than the value. Because those don't overlap, because those don't line up, we say then that no, it is not continuous. It is discontinuous. It's called a removable discontinuity because the point has been removed from the line and it does not work. What about at x equals negative 2? There's a real big problem at negative 2. At negative 2, we have an asymptote. Rule number 1 is that the function has to be defined at that point. It is not defined at that point. And because it's not defined, then, oops, I don't think I wrote it last time, neither of these are continuous. Let's do one more. Let's look at x equals negative 3. So negative 3, when x is negative 3, we hit this point on the graph. It is defined. And notice when we come in from the left, we go to the point. We come in from the right, we go to the point. Everything is satisfied. The limit comes in to the point. Yes, it is continuous at that point. So what we may be asked to do is to find out where a function is discontinuous. And again, it's just a vocabulary concept, is where is it going to be undefined? Where is the limit going to be different than the value when you plug it in? This is another funny way to ask the question, what is the domain? Think about how we did domains back in Unit 1. If we had f of x is equal to x plus 2 over x squared plus 5x plus 6. The rule for continuity is that it has to be defined at the values. Well, what makes a fraction discontinuous or undefined? When the denominator equals 0. So if we factor that to x plus 2 times x plus 3 equal to 0, we find out that x is equal to negative 2, and negative 3. At negative 2 and negative 3, because the function is undefined, the entire function is discontinuous as well at that point. Similarly, if I have f of x is equal to the square root of x plus 7. We know with square roots we are undefined if what's inside the square root is not greater than or equal to 0. Okay, so it's supposed to be greater than or equal to 0, but we're interested in when it's discontinuous, when it doesn't work. So that would be when it's less than 0. Subtract 7 from both sides. When x is less than negative 7, the function is undefined. Therefore, the function is discontinuous. We'll get to the real uses of this idea of continuous and discontinuous. Right now, I just want you to kind of start to wrestle your mind around the definition about, is it continuous at that point? Is there a jump in the graph at that point? Because jumps are bad. They make weird things happen. We don't like that in calculus. We want it to be continuous. So that's today's homework. Take a look at finding limits using all those strategies we talked about on your tool belt, and also playing with this definition and idea of continuity and discontinuity. We'll see you tomorrow in class to discuss questions. Take a look at the homework, and we will see you then.